All right, let's talk about something we feel every single day, but maybe don't really think about heat. It's this invisible force that's everywhere, warming our coffee, cooking our food, and even powering the weather systems of our entire planet. It's so fundamental, so let's dive in and really understand the story of heat. So let me ask you something. Picture this. You've just poured a steaming hot cup of tea, and you leave a metal spoon in it. You go to grab it a minute later, and youch! It's scorching hot and burns your fingers. But the wooden table that the cup is sitting on, perfectly cool? What is the deal with that? Stick with me because by the end of this, you'll know exactly what's going on. Okay, so to solve that spoon puzzle, we first have to clear something really important up. We use the words heat and temperature all the time, pretty much like they're the same thing. But in the world of science, nope. They are two very, very different concepts. Think of it like this. Temperature measures how fast a single particle is jiggling around. It's the degree of hotness, which we measure in Celsius or Kelvin. But heat is the total energy of all the particles in an object combined. So a tiny little spark can have an incredibly high temperature, but a big bathtub full of warm water has way, way more total heat energy. It's the difference between one super energetic dancer and the energy of the entire crowd. And here's a temperature you know like the back of your hand, 37 degrees Celsius, or as most of us know it, 98.6 Fahrenheit. That's our normal body temperature. It's just a specific measurement of how hot we are, not how much total heat energy our bodies contain. So now we know what heat is, but how does it actually get from one place to another? How does it move from that hot tea into the metal spoon? Or, think bigger, how does it travel from the sun all the way to Earth? Well, heat energy doesn't just teleport. It has to travel, and it turns out it has three main pathways. Yep, there are three major ways heat gets around town: conduction, convection, and radiation. We're going to break down each one, and I promise once you get these three, you'll start seeing them in action absolutely everywhere. First up, we've got conduction. This is basically how heat travels through solids. The best way to picture it is to imagine a bucket brigade, a line of people passing a bucket of water. The bucket is the energy, and the people are the atoms. The energy gets passed from one atom to the next, but the atoms themselves stay right where they are. And boom! This takes us right back to our spoon puzzle. Metals like silver and copper are fantastic conductors. They're like a super efficient bucket brigade. The heat from the tea gets the spoon's atoms vibrating, and that energy zips right up the handle to your fingers. Wood and plastic, on the other hand, are what we call insulators. They are terrible at passing the bucket along. That's why the wooden table stays cool. Next on the list is convection. This is what happens in fluids, so we're talking liquids and gases. Now, unlike conduction, where the particles stay put, with convection, the heated particles themselves actually get up and move. So forget the bucket brigade. This time, a particle grabs the heat energy and literally runs with it to a new location. You see this every single time you boil a pot of water. The water at the bottom gets hot, it expands, becomes less dense, and rises to the top. Then the cooler, denser water at the top sinks down to take its place, gets heated, and rises up too. You get that classic rolling boil. That's a convection current. And the same exact principle is what creates sea and land breezes, just on a much, much bigger scale. And finally, our third path, radiation. Now, this one is kind of wild because it doesn't need any particles at all. It can travel right through the empty vacuum of space. So if conduction is passing the bucket and convection is running with the bucket, radiation is just throwing the bucket clear across the room. The energy travels as waves, just like light does. I mean, the biggest example of all is the sun. Its heat travels 93 million miles through empty space to warm us up, and it's all thanks to radiation. You also feel it as that warmth that hits your face from a bonfire. And here is a super important detail for later. Dark-colored surfaces are great at soaking up this radiation, while shiny, light surfaces are awesome at reflecting it away. So we know that heat travels. But what happens when an object actually absorbs all that energy? Well, it doesn't just sit there. Heat is a force of change. It makes things happen. And the most common effect is a really simple but powerful physical change. When you heat things up, they expand, they get bigger. And when you cool them down, they contract or get smaller. It's called thermal expansion. Now, if you think that's just a tiny, minor effect, think again. In the blazing summer heat, long steel railway tracks can expand quite a bit, and in the freezing winter, they shrink. That's exactly why engineers have to leave small gaps between the sections of rail. If they didn't, on a hot day, that expanding metal would have nowhere to go and would buckle and bend. That would be a disaster. It's literally life-saving physics in action. But this whole expansion thing isn't just a problem for engineers to solve. Nope. In fact, we've gotten really clever and have figured out how to harness this force of nature in some of our most common technologies. Ever see one of those old-school glass thermometers? That's just mercury or alcohol expanding as it gets warmer and rising up the tube to give you a temperature reading. Or the thermostat in your house. It probably uses what's called a bimetallic strip. That's just two different metals bonded together. They expand at different rates, which causes the strip to bend as it heats up, and that bending action flips a switch to turn on your AC or your furnace. It's brilliant. Simple physics at work all around us. So, wow, we've gone from a simple hot cup of tea all the way to outer space and back. Let's boil it all down and make sure we have the most important takeaways. Okay, here's what you really need to remember. First, heat is total energy, while temperature is just the measurement of that energy's intensity. Second, heat travels in three ways: conduction through solids, convection through fluids, and radiation through, well, anything, even empty space. And third, when things absorb heat, they expand, a principle we use in all sorts of cool technology. We started with a question about a spoon, so I'm going to leave you with a question to think about. Based on everything we just learned about radiation and how different colors absorb or reflect heat, why do we all wear light-colored clothes in the summer and dark-colored clothes in the winter? You now have all the tools you need to figure that one out. Thanks for joining me.